Okay, let's talk about parallel circuits. Parallel circuits are going to be different from series circuits because they have more than one route for the electrons to travel. Now remember we said that our electrons are going to move out of the positive end of the battery and into the negative end, and they will only move if there is a complete path connecting the two. If at any point in time there is a break in the circuit or any type of gap or opening, all of the electrons will stop. So they are either all moving or none of them are moving at all. Now, when we look at this image, you see that we have more than one route. So when we say that they're either all moving or none of them are moving at all, what exactly do I mean by they? Now we have to look a little bit more carefully. The electrons, remember, are present in the wire. So the electrons in the wire will move as long as they are connected. So we have multiple wires here. So we have multiple groups of electrons that we can make that statement about. So multiple pathways mean that we have multiple options for our groups of electrons, or I guess the more accurate way to say that is we have multiple routes for the electrons to travel through. Okay, so in a parallel circuit, we have the same amount of voltage for all of the different devices. Now, if you'll notice on this illustration as we continue to look at diagrams throughout the notes, we will see that we are going to have one device on each of our little branches. So we are going to keep it that way. If we start adding multiple devices on a single branch, now we are creating a combination circuit, and we are not looking at those right now. So in this situation, if one of these goes out, the others are still going to work. Let's go ahead and talk about that for a moment, and then we'll take a look at our simulators so that we can see these electrons in action, okay? It says if one of our bulbs goes out, the others still work. Now remember, current is the rate of the flow of those electrons, so let's just review how the electrons are going to flow. They're going to move out of the positive end, so let's just assume that this wire right here was connected there. Okay, so out of the positive end of the battery, and they're going to move through the circuit and make their way back to the negative end of the battery. Now, as they move through the circuit, we get to this location here, and our electrons have a choice to make. This is what we mean when we say multiple pathways. Do my electrons choose to continue forward and go down this middle section of the top line here, or do my electrons choose to turn and go down this first line, which takes it through the first bulb? So let's get a vocabulary word introduced here. We are going to call these branches. Everywhere that the wire splits and we get a different line that takes us down a different route, that is a branch. So this particular image has 3 branches. This would be the first branch. So the electrons absolutely could choose to come through the first branch, through that first light bulb, and then they would make their way back to the battery. So there is one possible option for the electrons to travel that would allow it to complete the circuit, because the electrons would have a complete connection. They would indeed all move, and the light bulb would turn on. But what about the fact that we can have electrons continue down that top line? Well, the electrons absolutely can also choose to continue to go down the top line, and then when they get here, we have another branch, so they have another choice to make. They can choose to go down the second branch, make their way through this device, and then make their way back to the battery, or they can choose to stay along that top wire and then ultimately go down branch number 3, putting it through that last light bulb and then back to the battery. So when we look at our parallel circuit, we have electrons that need to cover all of the circuit simultaneously in order for us to have all 3 light bulbs turn on simultaneously. So this means that in order for us to light up all 3 bulbs, our electrons are going to have to kind of split up. So think divide and conquer, right? We need all of the electrons coming out of the battery to split up so that they make sure all three devices get some of that electrical energy. So multiple paths in order to complete our circuit, and our electrons are going to have to split out or separate into groups so that they cover all of the different options. More bulbs in this case, the electrons are going to move so that the amount of current provided to our light bulbs will be the same for all the bulbs, therefore they will all be equally bright. So let's go ahead and look at our simulator. I have my battery, it is connected. I currently have a parallel circuit where I have two branches, so my electrons can choose to go through this first branch here with light bulb number 1, or my electrons can choose to go through this second branch here and pass through light bulb number 2. If I wanted to add a third, I can do that, and even a fourth. I have enough room on this simulator. So we'll end up putting all 4 on there so you can see what happens. But simply looking at our little arrows that represent our current, you can see that our electrons are all bunched together coming out of that battery. But when we get to that first branch, you see them arrows are a little bit more spaced out. Again, they're trying to visually represent to us what is happening with our electrons. So in this case, they're showing us that the electrons are splitting so that some of them are going down the first wire and some of them are going down the second wire. Now, this is a direct current, so the quote-unquote direction that the electrons travel does not change. Once those electrons pick their route, they have no choice but to continue marching forward. There is no backtracking for our electrons. So these arrows are pointing in the same direction for the entire trip. Now, if I were to take a third light bulb and add it to our circuit, first off, it must have a complete path in order for the electrons to flow through those wires. So right now, these wires have electrons in them, but they are not currently moving because they are not connected to the high and low ends of that voltage source, so they don't move. Once I complete the connection, now all of those electrons in all parts of the wire for that last branch are now going to move. Again, you can see from the simulation that we have all of the electrons coming out of the battery, but then the current the current we can see is going to separate out so that it covers all 3 branches. If I wanted to add a 4th branch, I could do that. Notice that if I connect this top wire first, I have no current flowing through that section of the circuit because it is not complete over there. So if I take my wires and put a 4th light bulb on, I now have my electrons moving so that they are now splitting up into 4 different branches. All of the electrons are moving so that they all deliver that electrical energy. And notice that the light bulbs are all equally bright. We're going to get through we're going to talk about the specifics of what is being delivered and look at some numbers for that here in a little bit. But for right now, I just want you to visually recognize that the brightness of all 4 bulbs is the same. If I take my circuit and put it back to where it's only 2 bulbs, those 2 bulbs are just as bright compared to having all 4 bulbs, okay? The other thing that I would like to point out to you is that when we said that if one goes out, all others work, if I were to put a gap in this wire affecting that second branch, or the second branch which has our second light bulb, the others continue to flow. They have a route that allows them to go out of the positive end of the battery to the negative end. We are connected from high voltage to low voltage, so those electrons are going to move, okay? I could put a switch here, and that switch could be used to control this light bulb individually. I could add additional switches. And depending on those switch locations, they can individually affect a branch. So I can have this one off or on. I can have both of those off and the other two stay on. But notice what happens if I flip that switch. Now let's just look at this for a second. The location is key. These other switches over here that are on currently, they all have only one light on their branch. They also are on an individual branch, but this very first switch, all of the electrons move through that section, right? When we were focusing on our arrows representing our current, all of the electrons flow through there. So if I were to remove this line, none of the electrons have a complete path. So yes, if one bulb goes out, the others work, provided that this is a true parallel circuit. Each branch has only one light bulb, so each branch would then be affected individually, independently, okay? All right, so for parallel circuit, we say that our current is going to be shared throughout and our voltage is going to be constant throughout. And it looks like some of my little edits didn't quite come through when I brought this over. So give me just 1 second. I wanted this to be a single battery for us, just to give us a different look. There we go. So we have a single battery, so we have 6 volts available for this entire circuit. You see that they have numbered branch 1 and branch 2. Again, how are we supposed to know what to call number 1 and what to call number 2? Well, when we talk about our current is that flow of electrons, right? The rate of electron flow. And it's showing us the path out of the positive end through the circuit back into the negative end. Now, when our electrons go around the circuit, they're going clockwise in this illustration because of what direction forward, quote unquote, forward would be for our electric charges. So as we go around our circuit clockwise, when we come to a branch, the first branch we encounter will be branch 1. The second branch we encounter would be branch 2, and so forth. So the electrons are going to travel through this resistor, come out the other end, through this resistor, come out the other end, and then they will make their way back to the main wire and complete that circuit. So when we say that current is shared throughout, that's because our electrons have to split, and we've already discussed that in good detail with our simulation, so we will move on. Next, let's talk about our voltage. So voltage in this case is going to be constant throughout. Again, voltage is going to be that ratio of energy available from our electric charges. So let's look at what happens with our voltage in this type of circuit. Our electrons are going to come out of the battery. In this case, it will have all 12 volts. I'm sorry, this is a 6 volt battery. It will have all 6 volts available. The electrons are going to pass down this wire. And as the electrons that go down the first branch, as they reach that particular device, notice they haven't encountered any resistors yet. These electrons have not emptied any of their energy. They are still traveling with full cups of energy, so that ratio of energy per coulomb has not changed since it left the battery. So my electrons are going to fuel or feed some of their energy to this first resistor. Now, they have 6 volts available. Remember, we said an overall main idea is that they are going to use all of the energy as they go through the circuit so that when they return to the battery, they have 0 volts remaining. So if my electrons have 6 volts available, they are actually going to dump all 6 volts, I'm sorry the picture's a little crowded, all 6 volts into the device right here. I'm just going to give myself a space so that we can see what I'm writing a little better. So all 6 volts are going to get dumped into this device. So when my electrons come out of this resistor, they have 0 volts left. They gave all of their voltage away, so they are going to exit that device with none, 0 volts, okay? The electrons that chose to continue traveling down that top wire instead of going down branch 1, they continued along that top wire. They have not encountered any devices yet, so they are still full of their 6 volts. When they go down their branch, they are bringing all 6 volts with them. So when these electrons encounter this resistor, it only has the one resistor to fuel, so all 6 volts are going to be dumped into that device. So these electrons are going to exit with 0 volts available. So when we say that the voltage is constant throughout, because we are looking at very basic parallel circuits where there's only one resistor on each branch, in that particular case, all of the voltage is delivered to that one device, and so all devices will receive the full voltage available from that voltage source. So as we look at our electrons returning back to the battery, these electrons are returning empty-handed, these electrons are returning empty-handed. So this entire group, once they get back together, are going to have 0 volts available, and that follows that basic main idea that I introduced in the very first lesson, that the electrons will leave with all of the voltage and return with 0 volts. If we are calculating the total resistance for a parallel circuit, it is similar to a series circuit, but a little bit more complex. So instead of just taking the sum of our resistors and adding them up and getting our total, that doesn't exactly work here, because with a series circuit, if we just pretended to be one of those electrons, that individual electron would indeed encounter resistance from the first, and then again with the second, and then again with the third. So that individual electron actually experienced all 3 of those resistor values. For a parallel circuit, that's not what happens. In fact, the more branches that we introduce to the system, the less resistance those electrons are going to experience. So when we calculate our total resistance for a parallel circuit, if we are simply taking those resistance values, we are going to need the inverse of each of those values. Now notice that the formula says 1 over the total resistance is equal to 1 over R1 plus 1 over R2 and so forth. So you can see from the example problem over here, we are taking 1 over 10 plus 1 over 12 plus 1 over 15. All of those decimal values are then added together, but that leaves us with 1 over R. We never leave our answer as 1 over X. We always have to take the reciprocal of that in order to solve for just plain old X. So that's what they are showing you they have done here. They have taken 1 over 0.25 in order to get a total resistance of 4 ohms. So when you are calculating the total resistance for a parallel circuit, you have to remember that since this is 1 over your total, you will need to take the reciprocal of your previous answer. So I have 1 over RT equals some decimal answer. It's usually a decimal. After I add up my other resistor values. So I'm going to take that answer to the -1 in order to give me just plain old RT. So we've experienced formulas like this before. Just make sure that you are taking that extra step to get your total resistance. All right, so let's look at an example problem of a parallel circuit. Here they are asking us for lots of information, but that's just because we have two branches, so we have two different places that we can get some of our information. So let's just start off by answering the very first item on the list. What is the total voltage? In this question, I have two batteries. Those two batteries are working collectively to provide the voltage for the entire circuit. So these two batteries are going to add up for 6 volts. So the total voltage available is 6 volts. Now, on this question, it says V branches, and sometimes that needs a little bit of a verbal explanation. What they are asking for in this particular question is, what is the voltage through each of the branches? So you can see on the illustration, they have identified branch 1 and branch 2. So here is branch 1 and here is branch 2. So I am going to choose to go ahead and write this as two separate answers. Once you understand that it's the same voltage in all of the branches, then them asking for V branches makes perfect sense. But we're still learning, so I'm going to go ahead and clearly identify branch number 1 is going to have 6 volts, and branch number 2 is going to have 6 volts, okay? It should be the same voltage in both branches. Again, we only have one resistor on each branch for our questions. All right, so then it starts asking me about my current. Now, the handout or this example problem is kind of walking us through the proper way to do this. So if I have my resistance value provided on the problem, which it clearly is, if I have my voltage provided from my voltage source and I now understand that the voltage is the same everywhere, then when they ask me for my current, I am going to choose to use Ohm's law to calculate my current. So the current that travels through resistor number 1 is going to be the value of resistor number 1, which is provided here, 3 ohms, the voltage through or across resistor 1, which remember, this guy has not encountered any of the devices on the circuit yet. So it currently has all 6 volts available. It's going to dump all 6 volts into that device and then exit with 0 volts. So I know what my voltage is at this location as well. So my current is going to be 6 equals I times 3. So divide by 3. 6 divided by 3 is 2. So I have 2 amps of current that flow through that very first branch. Now, V equals IR is my formula in order to calculate my current through branch or resistor 2. This time I'm going to go ahead and do my algebra first. So if I want to find my current through the second location, it's going to be the voltage across the second resistor divided by the value of that resistor. So I2 is going to be, my voltage is 6. My resistance from the picture I see is 6. So my current through the second resistor is 1. Okay, now it's asking me for my total current. So if we understand that the current came out and then the current split into these two, I should be able to take my total current by simply adding these two currents together, right? They were all together. They split into the 1 and 2 branches. So if branch number 1 got 2 of them and branch number 2 got 1, then my total current should be 3. Okay. Now, let's go ahead and pause for a moment and let's talk about this current just a little bit longer. Oh, no, wait, just kidding. I'm going to go ahead and do my resistance because I'm going to need my value for that. Now, in order for me to get my total resistance, I'm going to go ahead and do resistance using the equation that we were given in the notes for parallel circuits. So total resistance is 1 over RT equals 1 over R1 plus 1 over R2. So let's get my total resistance is equal to the inverse sum. So we're going to say 1 over RT is equal to 1 over 3 plus 1 over 6. I'm going to get that answer. I'll go ahead and calculate that out for y'all and tell you what it is. 1 over 3 plus 1 over 6 gives me 0.5. And remember, this is 1 over RT, so I need to take this and I need to say 1 over 0.5 is going to give me R. So we're going to invert that, and I get my R total is 2. So 2 ohms is my total resistance, okay? Now, before we get to power, I want to pause right here and let's talk about some of the options that we have for calculating our totals. You need to be able to calculate total resistance even if you have other variables available. I would like for you to practice calculating it this way because you will be asked, what is the total resistance? And the only information I'm going to give you worth using is going to be your individual resistance values. So make sure you know how to do this. But I also want to point out to you that we could have used Ohm's law in order to calculate what our total resistance was here. If I were to look at the variables that I'm given, I know what my total voltage is, and at this point, I knew what my total current was, so I could have used Ohm's law using the total values to calculate my total resistance. I could have just said 6 equals 3 times R, divide by 3. 2 ohms is my total resistance, okay? So this is a way to check yourself if you are a person who likes to be extra cautious and double check your work whenever possible. This is an option for you to calculate your total resistance. I would recommend whichever is the least complex, whichever you feel more comfortable with. Unless we give you a question where you only have your resistance values, it is really completely up to you how you want to pursue the calculation. I just need you to know that there are choices. Both will work if done correctly, okay? If we knew our total resistance and we wanted to calculate our total current, we could also have used V equals IR, where we took the total voltage of 6, the total voltage of 2, and calculated our total I that way. So what if this question didn't ask for I1 and I2? What if it just asked me for VT, IT, and RT? Then I would have needed to calculate my total resistance using the 1 over formula. Then I would have used Ohm's law to calculate my total current. So it's really important that you understand what these variables mean, understand how the electrons are moving, what they are carrying, when and what and how they deliver the energy throughout the circuit, because that's going to help you figure out which formula is acceptable for me to use at this particular location given this particular information. All right. The last thing that it's asking here is for us to calculate our power. So I just kind of wanted to address that with you. I don't want you to forget power is a thing that we could be asked to calculate. So let's say that they ask for the total power used by this circuit. Remember, power is the rate at which work is done. So these electrons are performing work here on our devices. The electrons are going to be delivering voltage to our devices so that they can then work. So our power is I times V. So if we're calculating the total power, they didn't tell me a specific location, so I just made the executive decision. We're calculating the total power here for this entire circuit. So that's going to be my total current and my total voltage. You have to always use all totals if that's what you are calculating. So my total current, we said, was 3 amps, and my total voltage is 6 volts. So 6 times 3 is 18. So the total power for this circuit is 18 watts.